Good day everyone. Welcome again to the course of structural biology, and as you know we are going through structural biology techniques continuing with X-ray crystallography. Today we are going to learn something new from the basic subject, which is instrumentation of X-ray crystallography. Majorly the instrumentation is categorized as part of the production of X-rays, which is the source of X-ray. I have talked about it little bit. Today I will talk about it in detail. Then I will talk about collimator, something which is very essential, something which help focusing. Then monochromators, they are also playing very interesting and critical role, and at the end detector. So, our instrumentation part is majorly categorized in these 4 subheadings, but when I will talk about at the end, I will talk about the X-ray diffractometer and where these guys are and how they are actually composed into an unit. Let us start with X-ray source because it is X-ray crystallography. So, the source is the preliminary requirement. Crookes tube, also called cold cathode tube, is not important anymore, but they are historically important. They are the X-ray source used on early 1900s when the initial experiments of X-ray crystallography were used to be done. These tubes generated the electrons needed to produce X-rays by ionization of the residual air in the tube. If you remember, and I will go and talk about, nowadays we are using this cathode and anode, but that time they are using residual air in the tube. They consisted of a glass bulb with around 10 to the power minus 6 to 5 into 10 to the power minus 8 atmospheric pressure of the air. You could see the tube here. This is the construction of the tube. They had an aluminum cathode plate at one end of the tube and a platinum anode target at the other end. So, this is the construction. Crookes tubes were unreliable. They used to be used at initial stages, but then they did not continue with because they were not reliable. With time passed of their usage, the residual air would be absorbed by the walls of the tube, reducing the pressure. So, when the machine would be used multiple time, becoming older, then that time the residual air would be absorbed by the walls of the tube. So, the pressure would be reduced, and this reduced pressure would result in the increase of voltage across the tube that generate harder X-rays, and eventually with time the tube stopped working. So, that is why it was not a good system to continue with. Seal tubes, we talked about seal tubes, so I am not going into the entire details. They are one composition where the entire X-ray generation system is sealed into one unit, thus eliminating the need for vacuum pump, motor to spin the target, etc. So, it is a one composed unit where there is heated filament which emits electron by thermoionic emission. The electrons are accelerated by high voltage. There is a copper rod for heat dissipation, and X-rays produced when the high speed electron hit the metal target. But seal tube are also not the best things to use because because of overheating and then unable to produce high energy. So, especially in of our interest, when we are using it for protein, we need high energy, and seal tubes are unable to do that. So, you do not get good resolution. Rotating anode is what people are using. Rotating anode allow the electron beam sweep a larger area of the anode, thus redeeming the advantage of a higher intensity of emitted radiation along with reduced damage to anode compared to its stationary state. So, it moves, it rotates so that the heating is not in, when I say heating here, I mean when the electron is coming and hitting, it is not in one area. The focal spot temperature can reach 2500 degrees centigrade during an exposure, and the anode assembly can reach 1000 degrees centigrade following a series of large exposure. So, they are enough stable. Typical anodes are a tungsten rhenium target on a molybdenum core backed with graphite. Why? Because the rhenium makes the tungsten more ductile and resistant to wear from the impact of the electron beams. That is why it becoming more stable. And then the molybdenum conducts heat from the target. The graphite provides thermal storage for the anode and minimizes the rotating mass of the anode. This rotating anode are still used, and they are specially used very comfortably for home source. I talked about synchrotron. Synchrotrons are large tubular rings under high vacuum in which fundamental particles zoom at velocities near the speed of light. Bending magnet cost energy to deflect, change the momentum of all those particles. That energy gets returned to us in the form of intense electromagnetic radiation when the particles change direction. A lot of this radiation is in the X-ray band, and we can use it as remarkably powerful X-ray source. So, from where this story comes, when I talked last time, I told that synchrotron used to be the toy of physicists. Now it becomes more and more useful for others, and especially protein crystallographers are using it in a huge way. There are few reasons of that. One, as when they started, things were not even in control, and crystallographers do not know how to use it. But now, with several years of national facilities in US, Europe, and Japan, Australia, now people understood a lot about the bending magnet. So, they know from where the energy is coming, and they have developed windows from where they have quantified the amount of energy coming. So, this helps the crystallographers to use this facility more and more. And how synchrotron is even more useful beside what we say, I talked about quick data collection. So, remember, if I talked about the home source with rotating anode, which we used to use in 2010, 2015, it used to be taking 3 to 7 days for entire data collection, which means one frame used to be around, depending on the signal, 10 to 30 minutes. In synchrotron, it is around 5 to 10 seconds. That is really something. But beside that, another important thing which makes crystallography more fruitful with synchrotron is, as I talked about, one of the biggest thing in crystallography is to grow crystals. Sometime you grow crystal, but the crystals are very small, very tiny. With that tiny crystal, it is difficult to diffract them in home source, and in that case, when you are getting not at all diffraction or diffraction at 7-8 angstrom, you could very well improve it to 2 angstrom, 1.5 angstrom with the help of synchrotron. Also, for the data which you are collecting in home, the resolution in many cases improves. So, these are the facilities which we get in synchrotron. So, bending magnet beam lines in Brookhaven, which is Brookhaven National Laboratory BNL, the facility called NSLS, are 50 to 100x brighter than the home source. At Argonne, where fortunately I spent 6 years while doing my PhD, the bending magnet beams are at least 1000x brighter than a home source. But this is great, but this is even better with the use of wigglers and undulators. What they do, here in the bending magnet, the velocity is changing, electromagnetic radiation is produced, but these devices are designed to produce a lot more local deviation in the trajectory before returning to its original path. So, what they do, as it called as a wiggler, it does the what the word means, it wiggle up and down. So, it makes more deviation. Wigglers and undulators act as X-ray sources, much brighter even than the bending magnets. So, a typical undulator is engineered to extremely high tolerances, features superconducting magnets, and is a few meter long. You could see here, this is the schematics from SLAC Stanford, the synchrotron facility. So, Wiggler beamline at Brookhaven are about 10x brighter than the bending magnet beamline. So, it again change, and when you see 10x, 10x is not less, because it is 10x on top of what the synchrotron national facilities was doing. And then it comes to APS, the undulator beamlines are 10 to 100x brighter than the bending magnet. So, it is great. There are modern new facilities, modern sealed X-ray tube which are made of ceramic, their beryllium windows is visible, and you could see the anode type as copper written here, and focus types are labeled. Beside that, there are metal jet made of gallium, where they use liquid metal. So, remember the problem. The problem is, when in the seal tube it was continuously targeted, it was generating a lot of heat. So, to solve it, we changed to rotating anode, so that it would not expose same surface same time. Now, they are coming up with even smarter technology. They use liquid gallium. So, each time the metal become bringing new gallium to the surface. So, the surface is changing continuously. So, these are the new techniques. Coming to collimator. Collimator is a device that narrows a beam of particle or waves. So, the beams are coming generated by the X-ray source. Collimator is narrowing them down. This is to cause the direction of motion to become more aligned to a specific direction, so that they could hit the target in the X-ray diffractometer. So, you could see here the beams are coming here, they are in different direction and they are aligned here. This is the function of the collimator. Okay. In order to get a narrow focused beam of X-rays, the X-rays generated by the target material are allowed to pass through a closely packed metal plate separated by a small gap. So, I was showing you two metal plates. Instead of two metal plates, they actually use series of metal plates with some gaps. So, this is what actually used. So, the closely packed metal plates, they are separated by small gaps and they channelize the beams. The collimator absorb all the X-rays except the narrow beam that passes between the gaps. So, only which are allowed are actually going and working, rest of them are absorbed. Coming to monochromator, as you understand, the polychromatic rays are becoming monochromatic. A monochromator is an optical device that transmits a mechanically selectable narrow band of wavelengths chosen from a wider range of wavelengths available at the input. So, if you see here, it is wider, it becomes narrower with the help of a monochromator. The name is from the Greek roots mono, mono is single, chroma is color, and ater is denote agent. So, an agent which makes single color, that is called monochromator. Monochromator crystals partially polarize the unpolarized light. Monochromatization can be broadly divided into two classes. One interference filters and 2 crystal monochromators. Crystal monochromators again can be divided into 2: flat crystal monochromator and curved crystal monochromator. Coming to interface filter, filter exploit the X-ray absorption edge of particular element. It is very interesting, at wavelength longer than the absorption edge. When I say longer than the absorption edge, it means just above the absorption edge, the absorption of the X-rays are considerably less. So, it takes the principle that at wavelengths longer than the absorption edge, which is just above the absorption edge, the absorption of X-rays are considerably less, and at the reverse, at wavelength shorter than the absorption edge is quite high. So, this is the scenario of nickel. The absorption edge of nickel metal, which is 1.488 angstrom, lies in between K alpha, which is 1.542, we all know, and K beta, which is 1.392 X-ray spectral line of copper. You know, copper is used specially for protein X-ray, and very fortunate situation here that nickel, its edge is in between the K alpha and K beta, so they could easily separate them. Hence, nickel foil of an appropriate thickness is used to reduce the copper K beta X-rays. When it says appropriate, how you mean or how you understand which is appropriate thickness? I will answer. So, what is appropriate thickness? So, if you see, without filter you have K alpha and K beta both, but with filter K beta is nearly not there. So, you only get K alpha. That is the beauty of using nickel filter. Choice of filter material, how we could choose the filter material. The choice of filter depends on the anode material chosen in the X-ray tube. Like for copper, I have shown we use nickel, for cobalt we use iron, for iron we use manganese, for molybdenum we use zirconium, for chromium we use vanadium. The beam passes through the top filter, which is nickel in this case. Alternative metal foils can be set by rotation of the filter housing towards appropriate position. How? We will look at one position of the filter housing kept open for the case where no filter would be required. What we are talking about is this. If you look at this, you will see that there is 1, 2, 3, 4, 5, 6, and you could use different metal here, and by rotating them you could change the metal of your choice. Also, if you see one of them, this one kept blank, so that when you do not need any filter you still use this setup. So, this is the effect of filter. You will see where the different metal chromium, iron, cobalt, copper, molybdenum are actually filtered using different other metals. And if you see the thickness, in case of chromium it is 11, iron it is 11, in cobalt it is 12, in copper it is nickel which is 15, in molybdenum it is zirconium it is 81. So, why for let us say for copper this is nickel which is 15, and for molybdenum this is 81, nearly 5 times more. So, I have asked this question, how to choose the filter thickness. The thing is, if there is no rule, you have to do trial and error, and generally the things come that if you get K alpha by K beta ratio within 25:1 to 50:1 in between, then you choose that. So, the thickness is optimized based on the ratio of K alpha K beta percentage available. Interference filters, X-ray beam may be partly monochromatized by insertion of the suitable filter. As we talked about, a filter is a window of material that absorbs undesirable radiation but allows the radiation of required wavelength to pass. Interference filter contains several optical layers deposited on a glass substrate or transparent quartz. The specific performance characteristics of the filter are determined by the thickness of the optical layers. Like here, you see the interference filter. This is called green interference filter, because when red is coming, it is reflecting, blue is coming, it is reflecting, but green is allowed to pass. So, as discussed, X-ray filters were used to reduce the unwanted white radiation from the X-ray source and to eliminate the K beta radiation especially. The major drawback of filter is that the background radiation is still high and the transmitted radiation is still not monochromatic. So, that is what the problems, but mostly they use successfully. Crystal monochromators. Crystal monochromators are made up of suitable crystalline material positioned in the X-ray beam. By doing so, they help the angle of reflecting plane satisfy the Bragg equation for the required wavelength. The beam is split up into component wavelengths. Crystals used in monochromators are made up of material like sodium chloride, lithium fluoride, quartz, etc. Pyrolytic graphite can also be used for broadband and silicon could be used for narrowband. So, as I told, there are two type of crystal monochromators. One are flat and straight and another one is bend. The bend one is helping the circular light to diffract, and they are mostly working on protein. So, what are the advantage of monochromatic rays? They help in improving resolution, they minimize sample preparation, they improve signal to noise ratio, they analyze small samples, and they also help multi-spotting on the samples. They simplify the data processing because you do not get the interference of the other one. Now, coming to X-ray detectors. X-ray detectors are devices used to measure the flash, spatial distribution, spectrum and other properties of X-rays. Detectors can be divided into two major categories. One, imaging detector such as photographic plates, X-ray film, which is photographic film we used to use before. Now, they are mostly replaced by various digitizing devices like image plate or flat channel detectors, and those measurement devices called counter methods. The X-ray intensities can be measured and recorded either by, as I told, photographic method and counter methods. Under the counter methods, there are various devices: Geiger-Müller tube counter, proportional counter, scintillation detector and semiconductor detectors. Both these type of method depends upon ability of the X-ray to ionize matter and differ only in the subsequent fate of the electron produced. So, how the electrons are ionized and what are the things they are detecting, how sensible, that is the main factor here. Photographic method, you could see the incident rays coming, and under the Ewald sphere, which we are going to discuss later in the next class, there is a reciprocal plane and a photographic film is kept there. So, to record the position and intensity of the X-ray beam, a plane or cylindrical film is used. The film, after exposing to X-ray, is developed. The blackening of the developed film is expressed in terms of density, where D equal to log I0 by I. I0 is the incident intensity, I is the transmitted intensity, and D is the total energy that causes blackening of the film. So, it is basically the photo, like X-ray films you now see when it is used for the patients to take their condition of bone or something in the hospital. D is measured by densitometer. The photographic method is mainly used in diffraction studies since it reveals the entire diffraction pattern on a single film. As you could understand, it is time consuming and uses exposure of several hours. Now we have changed the spectrum. Now we have devices which does these things with much speed and accuracy. So, counter methods: Geiger-Müller tube counter. Geiger tube is filled with inert gas like argon. Central where anode is maintained at a positive potential of 800 to 1500 volt. The electron is accelerated by the potential gradient and causes the ionization of the large number of argon atoms. So, basically argon is inert, and that is why no like side interference would happen. This result in the production of avalanche of electrons, a lot of electrons that are traveling towards central anode, which is the target. So, this is the setup, this is the central electrode, and here you will see the counting circuit. When the electron come, they actually make the factor here towards detection. Proportional counter, the setup is similar to Geiger tube counter. Proportional counter is filled with heavier gas. So, they are also having xenon, krypton, which are heavier than argon. And why they use heavier gases? Because they are easily ionized, and we will come to here. I will talk about operated at a voltage below the Geiger plateau, means where it comes in the Geiger-Müller counter. The dead time is very short, 0.2 microsecond. It can be used to count high rates without significant error. So, if you see the voltage here around 250 to 500, whereas in Geiger-Müller it is around 800 to above 1000. So, the voltage is less, and you will see how it is like producing the region of limited proportionality. This is, if you compare, you will see the difference. Counter method 3, scintillation detector. In a scintillation detector, there is a large sodium iodide crystal which is activated with a small amount of thallium. When X-ray is incident upon the crystal, the pulses of visible light are emitted, which can be detected by a photomultiplier tube. So, useful for measuring X-ray of short wavelength. Crystal used in scintillation detector include sodium iodide, anthracene, naphthalene, and p-terphenol. If you look at here, they have the conductor pin which you could install any place. This is the anode, and you have the scintillation which is hitting the cathode, and these are the part of the photomultiplier tube which enhance the signal. Semiconductor detector, while X-ray falls on silicon lithium drifted detector and electron and hole. So, this is the PNP diode technology. Pure silicon made up with thin film of lithium metal plated on one end, and under the influence of voltage, electron moves towards positive charge and holes towards negative. So, there is a difference between the electrons and the holes. holes here working as a positive. Voltage generated is measure of the X-ray intensity falling on crystal upon arriving at lithium pulse is generated. Voltage of pulse Q by C, Q is the total energy collected on electrode and C the detector capacity. So, we talked about this 4 instrumentation. Now, as I told, I would talk about the X-ray diffractometer, how the whole thing is composed. A diffractometer is a measuring instrument for analyzing the structure of a material from the scattering, which means diffracting pattern produced when a beam of radiation or particle interacts with it. You have a material, you put the X-ray and it makes a scattering pattern or diffraction pattern. If the pattern would help you to calculate the property of this material, then it is useful. That is what happening in the diffractometer. A typical diffractometer consists of source of radiation, X-ray source, to choose the wavelength. Like when you are working with protein, you are using copper. Copper is 1.54 K alpha. Now, if you think this is copper, but you need 2 wavelength. Why? We will come when we are going to solve the phase problem. In next few class we are going to solve it. So, when we are going to take phase problem, we need a reference. So, instead of you have copper, you need another one. So, you have to choose that, right. It needs a collimator to make the beam parallel. We already know about collimator, we know how collimator works. So, diffractometer needs a collimator to make the beam parallel. It contains a setup of sample holding. If it is X-ray diffractometer where you are working with protein, you know that your protein crystals are fragile, soft and all. So, you need a nitrogen gas setup, you need the crystal to set up in a balanced way in the goniometer, so that you could change the angle of data collection automatically. So, all these are setup of the sample holding. It needs a detector to detect the diffracted signal, right. We talked about those detectors. An X-ray diffractometer illuminates the sample of material with X-rays of known wavelength. When you are sending the X-ray, you know the wavelength. A strip of X-ray film is mounted in circular position around the sample. The undeviated central beam passes through a hole E cut in the film strip P. If you take a film strip, like you take a film strip, there is a hole, it goes straight. Diffracted beam falls on the film at various points like D1, D2, D3, D4. So, you change it so that this happens, and intensities of the diffraction peaks are proportional to the fraction of the material in the mixture. So, you are getting it, and from the pattern you could calculate, which is what we are going to read in the next class. So, I have developed a simple instrumentation setup of the diffractometer. You need the electric power which go through voltage stabilizer and current stabilizer going to high voltage generator and coming to X-ray tube. It might be X-ray tube, it might be rotating anode, it might be synchrotron, it might be Wickler, it might be undulator, anything it needs the X-ray to provide. Then it goes through the slit, and the collimator which we talked about, the collimator will align it and then it hit the crystal and the detector is going to detect it. That is the basic setup, but in addition to that, now you have to get the signal. So, you have the amplifier, scaler, printer, rate meter and recorder, which are the secondary devices which will record the data. So, what next? We now would get the X-ray diffraction pattern from a single crystal, and if you look at this image, this image happens to be a 360-degree rotation in phi collected on a CCD detector with all goniometer angles set to 0. Note that the X-ray diffraction pattern from a single crystal is a set of spots. So, you could see the set of spots, and do we understand what is there? If you look at, you will get an idea of a periodicity, which is what we need. So, in the next class, we will talk about how this diffraction pattern used to be. In previous class, we discussed about the ordering of the crystal when we were talking about crystallization, that if there is translational or rotational degrees of distortion that affect the diffraction pattern. So, how the diffraction pattern will come, how we would use these to measure something, and how we get to solve the protein structure would be our future discussion. Thank you very much. You guys are lovely audience, and I hope that you understand from this class. If you have any queries, please let us know. I will try my best to answer. Thank you.